Welcome to the next session of model number 4, which is centroid. In the previous sessions we have understood about the centroid and we have also understood to derive the centroid for different plane figures. Okay, now let us move on to the numericals. That is, let us try to understand how to locate the centroid for a given lamina. So the problem goes like this. Find the centroid of the lamina shown in figure. So this is the problem number 1. Now we need to locate its centroid. So what are the steps involved in this? So there are basically 3 to 4 steps involved in this. If you find any axis of symmetry, that is any symmetrical part, then you need to draw that axis. The second thing is you need to write the referral axis. It is very much important because you are going to determine the centroid with respect to that referral axis. So it is very much important. And then the third step is you need to divide the figure into known components whose centroidal values are known. That is, we have already discussed that in the previous sessions. Okay, so we know the centroidal formulas for rectangle, triangle, semicircle, quadrant of a circle. So in this case, I can divide this into 2 different components. Can you guess which components I can divide this into? This can be divided into 2 different rectangles. That is, if I just draw a line here, this will be one rectangle and this will be another rectangle. So after dividing, we need to number it: component 1, component 2. Okay, so after you divide this into 2 different components, for your convenience, try to write the edges ABCD, rectangle ABCD. Now it can be defined as a rectangle ABCD. You cannot define rectangle 1, rectangle 2. It will be much easier. Yes or no? Similarly, the second component D, E, F, and this point I shall write as O because it will be acting as origin. I told you that the centroid should be located with respect to the referral axis. Hence, we need that O to be marked exactly at origin. Now after dividing this into 2 components, the next step is you need to draw its referral axis. Okay, so the referral axis should be drawn according to your convenience. Okay, so now in this problem, let me draw the referral axis with respect to point O, origin, and this will be OX axis and this will be OY axis. This will be OY and that will be OX. You need to determine the centroidal values, that is X bar and Y bar, with respect to these axes. x bar should be measured from OY axis, y bar should be measured from OX axis. But the thing is, you know how to calculate the centroid only for the rectangular components or regular geometrical figures. But here you need to locate it with respect to referral axis. But initially you are not having any idea about the referral axis. Here you need to measure the centroidal values from the referral axis. So you need to measure the centroidal axis with respect to OX and OY. But you know how to locate the centroid of rectangle components. So let me show you how to proceed with. So as I said, the first step should be finding out any axis of symmetry. The second step is write the referral axis, and you have already divided this into number of known components whose centroidal values are known to you. And this is a rectangle, and you know the rectangle centroid lies exactly at center. Okay, always try to follow x into y dimension, horizontal into vertical. Please follow this, it will be much easier. Okay, so after dividing this into two different components and writing the referral axis, next is we need to calculate the areas of two different components. So here we have divided this into two different rectangles. Now we shall determine its areas and corresponding centroidal values. So for the first component, component 1, which is a rectangle A, B, C and D. And what are the dimensions? X dimension is 20 mm. What about its Y dimension? As you can see, from top to bottom it is 100 mm, but we have divided this into different components, and hence 100 mm is from point A to point O. I need to measure from point A to point D, that is 80 mm. Now, where does the center of this rectangle lie? That is exactly at center. So this will be x component of this component 1, and this will be the y component of this rectangle. Correct? So if I write the area A1, area of the component 1, A1 is equal to length into breadth, that is 20 into 80, which is 1600 mm square. What about the x of this component? It is half of 20, which is 10 mm. Y component of this, it is 80 by 2, half of 80, which is equal to 40 mm. Okay, for timing, let this be the details of component 1, A1, x and y values of component 1. Similarly, let us calculate the component 2 area x and y. So for component 2, the rectangle looks like this, that is DEFO, D, E, F and O. So dimensions, this is 80 mm, this is 20 mm. So where does the center of this component lie? It lies exactly at center. So what is the x value from here to here it is x component, and from here to here it is y component. Okay, so if I try to write the area of component 2, it will be A2 will be equal to 80 by 20. Again it is 1600 mm square, and x is equal to half of 80, 40 mm, and y value half of 20. This is how you write the centroidal components of different figures which you have divided. The next step will be try to measure the same components with respect to this referral axis drawn, which is OX and OY. Here there is no question of referral axis, it is the centroidal component for a given figure, but try to locate this with respect to the axis given. So, with respect to this axis and this axis, what are the values of the centroid? That should be the centroidal values of component 1. Similarly, for component 2, place that above the axis, referral axis, and try to locate its centroid. That can be taken as x1, x2, y1, y2. Clear? I hope you have understood. Now, to make it simpler, let me write this data in a tabular column. That will be much better. Okay. So, this is only for your reference, how it is determined, how the centroidal components of individual figures whose centroidal values are already known are determined first, and then you have to place it on the referral axis and try to locate the or measure the centroidal values. Okay. So, the first column be component, the second column be area in mm square, the third column be its x with respect to the referral axis, the fourth column be its y value with respect to the referral axis. So, this is nothing but x bar and y bar of different components. Component 1 is rectangle A, B, C, D. So, what is area? We have already calculated, which is 1600 mm square. And what about the x value? That is x value of component 1 with respect to this referral axis. Please be careful. That is with respect to OY axis. Let me write OY axis and OX axis. This is very much important. You have to keep this thing in mind. Okay. So, OY axis, the distance of x is x1 is equal to 20 by 2, 10 mm, and its y1 value. So, now if you measure it from this axis, OX axis, where will it be located? So, it will be 20 plus 80 by 2. Okay. So, that is 20 plus 80 by 2, which is equal to 20 plus 40 which is equal to 60 mm. I have already mentioned the unit mm above. So this is the value of x1 and y1 with respect to the referral axis of component 1. Now draw this line. Next, component 2 is DEFO. So what about the area, which I already calculated? 1600 mm square. X2 is to be measured with respect to the referral axis, which is OY. From this axis, what is the value of x? So the previous one which I already written, try to write or keep it above the referral axis. So therefore this will be the centroidal value x2, that is 80/2, 40 mm, and y2 with respect to OX axis exactly at center. So this will be y2 20/2, which is 10 mm. For your convenience, you can also draw the shape if you want. This is a rectangle, again this is a rectangle. So to be precise, you can even draw the exact shape. Rectangle, correct? You are left out only with the calculations of actual x bar and y bar. So this x bar and y bar are the values calculated with respect to referral axis for different components. So using this table, I can locate x1 and y1. So this is the centroid of this component. So this will be x1 and this will be y1. Similarly, this will be the centroid of this rectangle. So therefore this will be x2 and this will be y2. These values needs to be calculated. But to calculate these values, the step done previously will help you out. Okay, calculating the centroid for different components, then try to measure it with respect to the referral axis. So now by using this table, we can calculate x bar and y bar of the entire lamina. Okay. So now let me erase this. X bar is given by A1 x1 plus A2 x2 divided by A1 plus A2. Now this will be equal to A1 is 1600 into, what about x1? x1 is equal to 10 mm. So it is 10 plus A2 1600 into x2. See, this is x2, which is equal to 80/2, 40 mm whole divided by 1600 plus 1600, which is equal to 16,000 plus 64,000 whole divided by 3,200, which is equal to 80,000 divided by 3,200. So this will be equal to 25 mm. X bar will be equal to 25 mm. Similarly, if I calculate y bar, which will be equal to a1 y1 plus a2 y2 divided by a1 plus a2, which is y bar equals to 1600 into y1. See, this is the total y1, so it is 20 plus half of this 80, which is equal to 20 plus half of 80 is 40, it is 60 mm. Plus 1600 into y2. y2 is half of 20, which is 10 mm. Whole divided by 1600 plus 1600, which is equal to 96,000 plus 16,000 divided by 3200, which is equal to so cancelling and calculating the value of y bar, we obtain this y bar equals to 35 mm. Okay. So at last you have calculated the coordinates of the centroid G of x bar comma y bar, which is equal to 25 comma 35 mm. So these are the coordinates of the centroid of this particular lamina given. Now try to locate this in the actual figure. So from point O, 25 mm x, so somewhere here, and y 35, 20 plus 15. So this is the centroid G of x bar comma y bar. This is the centroid of the lamina. Now you have to draw the axis, centroidal axis. So draw the x axis line, which will be xx, and correspondingly draw its y axis, which is called as yy. This is the location of the centroid. Okay, now we have determined the location of the centroid of this given lamina, and you know what? The position of this lamina will not change even if you change the orientation of this figure. Even if you change this to any other direction, this location of centroid will not change. You might get different values of G. You might get different values of G. Number might vary, but the position will not change. So you can take it as an assignment that and try to change the orientation of this particular figure and try to calculate its centroidal values and also the location of centroid. Please try it, then you will understand clearly that the position of centroid will not be changing, but the values or the number might be changing. This might change because you are going to take it or measure it with respect to the referral axis which you draw. That's why this might change, but the location of the position of the centroid will not change. Okay, so this is the first problem. I hope you have understood this. So this is a very basic one, very simple problem in which you have both x bar and y bar. So in the next sessions you will be having problems, all the numericals, wherein you might have only one axis because the other axis will be symmetrical. You will be having an easier way to locate the centroid. Okay, so for that you need to understand what is the axis of symmetry. Now we shall go on to the next problem, problem number 2. Okay. Find the centroid of the lamina shown in figure, and the figure goes like this. So, this is the problem given. We need to locate its centroid. So, now you might have understood what are the steps involved in it. What are the steps involved? The very first step is try to find is there any axis of symmetry. Then the second step is write the referral axis. Then third step, divide the components into different components whose centroidal values are known to you. Again, at last calculate the x bar and y bar using the formulas. Okay. So, for this particular figure, the very first step is try to find if there is any axis of symmetry, that is mirror image of other. One part should be equal to the other part. So, if I draw an axis exactly at center of this figure, I can easily say that one half is equal to the other half, that is mirror image of the other. And this will be y axis. So, the lamina is symmetrical about y axis. So, what does this mean? If it is symmetrical about y axis, that means there is no x bar, you will not be getting any x bar value. Therefore, the lamina is symmetrical about y axis, therefore x bar is 0. This is the point to be kept in mind. Okay? This is the advantage that you can take for the symmetrical axis, and also this axis gives you an idea that the centroid of this lamina will be lying somewhere along this line. This symmetrical axis gives you an idea about the point that the centroid of this whole lamina will be lying somewhere along this line. Okay. So, that is the hint that you can obtain from this symmetrical axis. Okay. So, now we have drawn this symmetrical axis. What happens if x bar is 0? So, that will give us a hint to select the coordinate axis or the reference axis as well. Okay. So, if you choose this point as origin instead of the starting point, then only we can say that x bar is 0. But if you choose this as the reference point, then we should be writing x bar should be equal to some number. Okay, it is not 0. If you write the origin at this point, then we can say x bar is 0. If you write the origin at this point, then we will be having the x bar value and it is not equal to 0. Okay. So, please keep this thing in mind. If you write the origin here, then the x bar value will be exactly half of the 150 mm, that is 75. So, x value will be 75 mm, or if you choose this as origin, then only we can say x bar is 0. Please make note of this point. Now let us divide this composite section into different components, regular components whose centroidal values are known to you. So if I divide this, so this will be number 1 and this will be number 2. Rectangular component 1, rectangular component number 2, and let me write A, B, C, D, E, F. I am not using G because it is to be used for centroid, H, and E, F, G, H, I. Now let me choose this point as origin O, and now let me write the reference axis. OX, this is OY. So the already existing YY axis can be taken as OY axis. Okay. Now writing the component 1, area A1. To write area A1, let me plot the figure, which is A, B, C and D, and also the dimensions 20 mm and 100 mm. And where does this centroid lie? Here, since we are taken the origin exactly at the center, so no need to write x value, only plot or write the y value, that is centroid of this particular rectangle and only the y value. So A1 will be equal to x into y, it is 20 into 100, which is equal to 2000 mm square, and y is equal to half of it, that is 100 by 2, which is equal to 50 mm. Okay. Now let me write component 2. That is E, F, H, I. This is 150 mm and this is 20 mm. As I said, do not write the x value because it is exactly lying in center, and the y value of this rectangular component is 20 by 2. So you can write A2 is equal to 150 into 20, which is 3000 mm square, and this y is equal to 20 by 2, which is equal to 10 mm. See, there is no need to write component 1 and component 2 details in this manner if you write the table, which I will be writing next. Why I have written this component 1 and component 2 separately? That is in order to make you understand how separate or individual centroids of those components be located. And then after calculating this value, you have to place it along the referral axis and then measure the required centroidal distances. Okay, for that it will be very helpful. Now let me write the table. We already know x bar is 0, and here this is the referral axis OX and OY, not the first point. This is taken as origin O, that is why x bar is 0. This has origin, x bar will be equal to 150 divided by 2. Please be careful with the coordinates. Okay. So now the first column is component, second column is area, mm square, x bar in mm with reference to OY axis, and y bar in mm with respect to OX axis. Now, which is component 1? Component 1 is the rectangle ABCD. The rectangle is like this, and area (2000 mm square). Then we are making the entire x bar column 0 because it is symmetrical about y axis, and then we can write y1 that should be measured from OX axis. So, from this line to this point, though the centroid of this component is at this center, you need to measure this from the referral axis, which is y1. So, if you look at this particular figure, y1 will be equal to the distance from this point to this point, that is from H to F, which is 20, plus half of B to C, that is 100 by 2, which is equal to 20 plus 100 by 2, which is equal to 20 plus 50 is equal to 70 mm. Y1 is 70. Now, let us take the second component, E, F, H, I, and the rectangle is like this. Its area 150 into 20, which is 3000. Okay. Next, 150 into 20 is 3000. And what about y2? Y2, that is, locate the center of second component with respect to the referral axis. So, this will be y2. So, what is y2? Easily you can say half of it, that is equal to 20 by 2, which is equal to 10 mm. Since x bar is 0, just calculate the y bar using the formula y1 plus a2 y2 divided by a1 plus a2, which is equal to 2000 into 70 plus 3000 into 10 divided by 2000 plus 3000, and this works out to be 34 mm. Y bar will be equal to 34 mm. Okay. So, last, therefore, G of x bar comma y bar is equal to 0 comma 34 mm. This is the centroidal value of this entire lamina with respect to the referral axis which I have drawn. So, 34 0, where does 0 lies? Exactly at origin, 0, x is 0, and what is y? Y is 34. So, you have 20 and plus 14, somewhere around here you can locate the centroid of the entire lamina G, that is x bar comma y bar, which is 0 comma 34. Now, you can write this x axis. This is the centroidal axis, x axis and y axis of this particular lamina. I hope you have understood this. See, in this problem, we had one of the axes to be symmetrical and we have taken the advantage of it. Since we have taken the advantage of that, x bar is written as 0 and hence choose this as the origin. This is applicable only when you choose this as origin, but if you choose this as origin, we will be having the x bar value and it will not be equal to 0, it will be equal to 150 divided by 2, which is 75. So, from here if you measure x, this is 75 mm and 34 mm is y. See, that is the speciality of centroid. Even if you change the reference axis, the numbers might change, but the position will not change. See, the position will stay here itself. Even if you change the orientation of this figure, then also the centroid location will be at the same point. It will not be changing or shifting to some other point, but these coordinates might vary. Coordinates might vary because we are varying the origin as well, that is reference axis, but the location of the centroid will not be varied, it will be at that same point. If you shift this origin to the first point, then you will be having x bar is equal to 75 mm. So, x is 75, y remains same 34. So, obviously this location will not be altered. This position will be the same, but the coordinates of this might vary based on the reference axis you choose. I mean to say the coordinate axis. So, here we have located the centroid of a composite section. So, how do we locate the centroid of a composite section? That is, we need to divide this into two different components which are regular geometrical figures whose centroidal values is known to you because we have already derived it. Since it is a rectangle, we know the centroid of a rectangle lies exactly at center. By taking the advantage of that, we have tried to locate the centroid of the entire composite section. Okay, clear? So, now we shall move on to the next problem. So, now for third problem, what I will be doing is, let me take up the first problem itself and try to change its orientation, and then let us see whether the centroid of that lamina will be at the same point or will be changing. As you all know, it will not be changing, but we should understand it with the help of a problem. Then only you will understand it better. Yes or no? So, you need to understand by taking an example, and then you can easily say that even though the orientation of a lamina is changed, the position of the centroid will not be changed. Okay? It will be exactly at the same point. The location of the centroid will not be changing, but the coordinates might be varied with respect to its coordinate axis or the referral axis. Okay? So, if you find the similarity between the problem number 1 and this problem, you had this orientation of the lamina changed in the first problem. Just I have changed the orientation of the same problem, and let us try to understand how the centroid can be located and whether the centroid position will be changed or not. Okay? So now, as we know the steps to be followed, what is the first step? See if there is any axis of symmetry. If not, go for the second step. Take the referral axis or the coordinate axis. The third step, divide the composite section into known components, number of components which are regular geometrical figures whose centroidal values are known to you. Then it will be very easier for you to locate the centroid, and then write the tables, calculate the areas of different components, try to locate the centroid of different components individually, and then try to replace that with respect to the referral axis, and then measure the centroidal distance with respect to the OX axis and OY axis, and at last using the formula for the centroid of x bar and y bar, substitute that and calculate the x bar and y bar values. So now let me take this as origin and this as OX axis and this as OY axis. So do you find any axis of symmetry here? Any symmetrical axis? No. So we can do is we can write the referral axis, and next we shall divide this into known components. So let this be component number 1, component number 2. Okay. So what about the size of component 2? Here it is given as 100 mm, but since we are dividing this component, this will be now equal to 80 mm. Okay, 80 mm. Now we have divided that into two components. Try to plot the centroids of two different components, then you can plot the centroid of the whole lamina. Now what is the first step? For component 1, this is the rectangle of size 80 mm by 20 mm. So for your convenience, we can also name the rectangle as A, B, C, D, and D, E, F and O. There are two different rectangles here. So this will be A, B, C, D. So area 1, A1 is equal to 80 by 20. Always do x into y. That is 1600 mm square. Its centroid x, which is this point, that is x. What is x of this rectangular component? It is 80 divided by 2. Which is 40 mm. What about y? The distance from here to here is the y component, which is equal to 20 by 2, which is equal to 10 mm. Similarly, I shall take up component 2. So the component 2 is oriented like this: D, E, F, O. The dimensions are 80 mm and 20 mm. So try to locate the centroid. So this will be the x component of this rectangle and this will be the y component of this rectangle. Now calculate its area A2, which is x into y, 20 into 80, 1600 mm square, and then x of second component will be equal to 20 by 2, which is equal to 10 mm, and y is equal to 80 by 2, which is equal to 40 mm. See, again you can eliminate this step and go directly to the next table, but why I am making you write this is so that you can easily understand to calculate the centroid of individual components first, then try to plot it on the reference axis or the coordinate axis, and then measure the centroids from OX and OY. Okay? Now let me write the table. Area mm square, x bar in mm with respect to OY axis, y bar in mm with respect to OX axis. So component 1 is AB, CD, the orientation of rectangle is like this, area 1600, and x1 is to be measured from which axis? OY. So from OY, try to locate its centroid. This is what? x1. So x1 from this axis will be 80 by 2, which is 40. What about y1? So the same point, you had only calculated this distance, but you need to measure it from this line. This is y1. So what is y1 now? From this point to this point, that is from F to E, it is 80 plus half of it, 80 plus 20 by 2. 80 plus 20 by 2, which is equal to 80 plus 10, which is equal to 90 mm. Second component is DEFO. The orientation is like this, and its area is already calculated, 1600. Now coming to its x2 value, x2 should be measured from OY axis. So x2, from this axis measure the centroidal distance x2 for the second component. So this will be equal to half of 20, which is 20 by 2 equals to 10. What about y2? Coming to y2 with OX axis, this is y2. 80 divided by 2 is y2, which will be equal to 80 by 2 is equal to 40. Now we can easily calculate the x bar and y bar. So x bar is given by a1 x1 plus a2 x2 divided by a1 plus a2, which is equal to 1600 into x1 is 40 plus 1600 into x2 is 10 divided by 1600 plus 1600, which will be equal to and this will be equal to 25 mm. Next, we shall calculate y bar, which is given by a1 y1 plus a2 y2 divided by a1 plus a2, which is equal to 1600 into y1 is 90 plus 1600 into y2 is 40 divided by 1600 plus 1600, which will be equal to plus divided by 3200, which will be equal to 65 mm. This is 25 and 65. What about the values in the previous case, that is problem number 1? It was 25, 35. Now let us plot it. So x bar is 25 from this point 25, okay, and y bar is 65. So from here 65. So it is 80 somewhere around here. So let me plot it here, which is 25. Okay, no, not here, here. So this is our point G of x bar comma y bar. Okay, so now let me write the centroidal axis here. Xx, yy. So this is the point which is the centroid. See, even in the previous case, that is first problem, we had located the centroid in the same point. The centroid was located on the same point. Okay, but in this case, what has changed? Only the coordinates of centroid has been changed, but the position remains same. The position is not changed. I hope it is clear. So by this we can easily say that the centroid position will not change even if the orientation of the figure is changed. Okay.